Integration by partial fractions, part 3, quadratic factors. What if we had the integral 2x minus 1 over x cubed plus x dx? Now we know that the denominator is easily factorable, so I will rewrite it in its factored form. I can pull out an x, which leaves me with x squared plus 1. Is this integration by partial fractions? And the answer is yes. We have a linear factor and we have a quadratic factor. That is, we cannot factor that second piece anymore, at least not using real numbers. So the technique for doing partial fraction decomposition when we have a quadratic factor is pretty similar to when we have linear factors. I know that I will have some number over x, just like we did with our linear factors. That is, I have a 1 degree term less than my linear term, which means that my quadratic factor, having a 1 degree term less than the quadratic, must be linear on top. So that is how we handle partial fraction decomposition when we have a quadratic factor. I'm going to do the work on the side, that is, I'm going to find a, b, and c, and then I'll plug back into the integral at the end. So just like with linear factors, we're going to find the common denominator. I'm going to multiply the a over x times x squared plus 1 over x squared plus 1. We will multiply the bx plus c times x over x, which gives me the common denominator of x times x squared plus 1. And we're going to ignore the denominator and just solve across the top. Now notice here, I cannot use the version where I plug values in. Well, I guess I could, but I don't have a simple one for this term. Like, I can't plug in -1 to get a times 0. So I'm going to do the other one where I set up a system of equations, where I have ax squared plus a, that is, I'm going to multiply all of these things out, plus bx squared plus cx equals, and watch what I do here, 0x squared plus 2x minus 1. And I'm going to compare like terms on the left, starting with my squareds, that is my x squareds, which gives me ax squared plus bx squared equals 0x squared. I'm going to look at my linear terms on each side. That's going to give me cx equals 2x. Then I'll look at my constant term on each side, which gives me a equals -1. And once I know that a equals -1, I know that b equals +1. So I can plug these values back into my integral. That is the broken down integral part, where I have a over x plus bx plus c over x squared plus 1. Let's take just a little time to talk about how to integrate this second part over here. I'll leave the first part alone for now. When I integrate, I go through the process. Do I know the antiderivative? No. Can I rewrite it in a way that helps? Yes. Very often that's splitting up a fraction or distributing or something along those lines, something basic algebraically. Notice that we are allowed to split up that integral into x over x squared plus 1 plus 2 over x squared plus 1. And each of these parts has a different technique for the antiderivative. So let's go ahead and look through it. Let's take antiderivatives. The first piece is a natural log. We'll put the absolute values around the x. The second piece right here is a u substitution. So if you'd like, I'll do it over here on the side. If I were to just integrate this piece here, I would do u equals x squared plus 1, du is 2x dx. I'm missing a 2. I'm missing a 1/2 to fix it. So that part of the integral becomes 1/2 du over u, which I know is natural log. So plus 1/2 the natural log of u, I'll back substitute. I don't need absolute values because x squared plus 1 is always positive. And now I can look at this last piece. This is one I just have to know. It's arctan of x. In fact, it's 2 times arctan of x. And I'll slip in the constant of integration, c. What if we had repeating quadratic factors? The algebra of this gets very messy, so I'm just going to show you how to do it. I'm not going to work through the problem. But just imagine that we had the integral x squared plus 3x plus 5 over x plus 1 times x squared plus 4 squared. To break this down, we would do some number over x plus 1. We would do a linear term over the x squared plus 4. And then we would need a second linear term over the x squared plus 4 squared. Finding a common denominator, that is just imagining I'm looking at the numerator of something with a common denominator. I would have a times, let's see, x squared plus 4 squared, because that's what the a piece is missing. And then the bx plus c is missing an x plus 1 and one of the x squared plus 4s. And then the dx plus e is missing the x plus 1. After multiplying all that out, I would set it equal to the numerator of the original. Just because I worked ahead, I know I would need a 0x to the 4th, a 0x cubed, plus 1x squared, plus 3x plus 5. And this is one where I would do a system of equations with potentially 1, 2, 3, 4, 5 equations. If I was allowed, I would use a calculator to solve for those things and then plug back in to solve the integral. But again, all I wanted to do was set it up because you see how messy this gets. If you so desire, feel free to work out all the algebra.